Good morning all. SRM Institute of Science and Technology welcomes you all to the webinar on computer system problems and research. Now I request our beloved HOD ma'am, Dr. S. Prasanna Devi to present the welcome address.
Very good morning, ladies and gentlemen. I take immense pleasure in welcoming you all to this webinar on systems problem and research, organized by the Department of Computer Science and Engineering, SRM Institute of Science and Technology, Vadapalani campus. I'm duty bound to thank our management and dean, Dr. Durevelu, for supporting us to host this webinar today. I'm happy to welcome our speaker, my best friend, Dr. Ramkumar Jayaseelan, for this webinar. We are all aware that computer science and engineering is an area of very intensive research and development. It is estimated that the half-life period of probably the knowledge in this area is only about maximum of 12 to 18 months. So no other branch of science has such a short half-life period. So therefore, new problems have to be solved. At the same time, some of the old open problems also must be solved. This invited talk aims in addressing such open problems in systems and solutions. To address this topic, I'm sure we cannot have a better resource person than Dr. Ramkumar. Personally knowing Dr. Ramkumar, I've seen him grow as a passionate researcher. To tell about his passion, I can cite in small incidents that happened way back in 2004 when we were in our final year at the College of Engineering and our university. Microsoft came for our campus interview and most of us got rejected at the first level. There were multiple rounds of interview and for the final round, only 4 members were actually shortlisted. The interview happened at Park Sheraton till midnight 12 and finally 2 members got selected and we were happy that Ramkumar was one among the 2. The next day, we were happy and started congratulating Ram. To our shock, Ramkumar told us that he's not interested to take up that offer because it didn't have much scope for research. So then Ramkumar got selected for the direct PhD after BTech at the National University of Singapore. That too in his most favorite and awaited topic in the thermal management of microprocessors. His passion never stopped with his PhDs. Many times I've heard Ramkumar telling us that he does not have any challenging work in research to do while he's working at his earlier companies. He's one person who always looks for a research component in every aspect of his work. Also, I'm proud to inform that to most of us in our entire batch, it was Ramkumar who taught us advanced computer architecture. I really owe all my knowledge in pipelining, scheduling, and all the other topics in advanced computer architecture only to Dr. Ramkumar because he never taught us the subject from the book. He taught us the implementation using a simple scalar tool. And that time we had to do it practically and for the study of advanced computer architecture. So that actually gave us the complete transformation from dislike of a subject to my favorite subject. All this simply means that Dr. Ramkumar is just not a passionate researcher, but he's also a lovely teacher as well. I'm sure that the next 1.5 hours would be a most interesting talk for all the participants. Finally, I also welcome all the enthusiastic faculties and research scholars attending this webinar. And I'm very sure that you'll have a great learning experience. Thank you all for attending this webinar. Wish you all good learning experience. I now request Ms. Ramya to introduce the speaker for the day. Ramya?
Yes, sir. On behalf of SRM Institute of Science and Technology and Department of Computer Science, it takes me immense pleasure to welcome Dr. J. Ramkumar Jayaseelan. Dr. Ramkumar is currently working as server performance architect in AMD with good understanding of workload, system architecture, and CPU, fabric, and memory microarchitecture. He has pursued his BTech in computer science from Anna University and PhD in computer science from National University of Singapore. He started his career as an intern in Google USA and as staff engineer in Qualcomm, acquiring expertise in server performance modeling and architecture, modeling coherent states, workload analysis of distributed and multi-threaded workloads. He has also worked on performance analysis, modeling, and feature analysis for both server, HPC, and client workloads. He has a good exposure in designing features and understanding the bottlenecks of classic workloads, as well as emerging workloads such as distributed system workloads, deep learning training, and GPU accelerated workloads from NVIDIA. His key achievements are analysis of server workloads and performance in AMD new server platforms, understanding system-level performance bottlenecks of GPU-accelerated workflows such as deep learning training, SM architecture, and perf analysis, low precision and deep learning training, and more. He is the key contributor in a team that developed SoC level performance and power models like multiple IP use case power or power performance analysis and feasibility study and analysis. He is skilled in competitive analysis of hardware, compilers, and micro benchmarking. His areas of specialization are memory QoS features development and evaluation for hard real-time clients, CPU path latency and coherence features development and analysis, development modeling and of SoC level power and thermal management algorithms, CPU features exploration, modeling and correlation, workload analysis with focus on client benchmark and spec, performance analysis of system workloads, and finally, application specific thermal management of microprocessors and more to add on. Learn as though you would never be able to master it. Hold it as though you would be in a fear of losing it. With this note, looking forward for a great session with you. We welcome you, sir. The session is over to you, sir.
Okay, I just wanted to make sure that as you could hear me. Okay. So I have a few slides. Thanks a lot for the introduction, and yeah, thanks. I'm happy to be presenting here, and yeah, so I just walked through. I have a few slides. I probably have about 15, 16 slides. So just feel free to interrupt. I've kept it fairly high level, and if there's any particular thing we want to talk about in more detail, we can talk about that. I think we'd be happy to talk about that. So I think so I'll just jump into the outline. So uh, yeah, so yeah, I mean, I've spent most of my time kind of working on the performance side, trying to understand uh, the performance of various workloads and trying to get performance better with every generation, either through hardware or software. So most of this talk would be kind of touching on the performance aspects of computer systems in general, right? So what I wanted to start out with is two different use cases, right? So first one is kind of so when you talk about performance, there's two aspects to it. The first is latency, which is how much time it takes to do a particular thing, and the second is throughput, which is how many things can you do in parallel, right? Uh, and so I'll start off with a use case which talks about latency, and then we'll go through. And then I'll talk through what the key issues when you're trying to kind of minimize the latency of a system, and then we'll go through a system where throughput is more important and what are the main issues there, and if there are any questions or I mean, if you want to cover any of those topics in detail, we can certainly do that. So okay, right. So to start out on the latency, and so I've kind of mostly focused this on what happens in large server data centers and places with a lot of servers, right? So I think very common use case that we kind of see with the mobile phones and all of that today is okay. So the mobile phones and all of those today is kind of you have an end user using a very simple very simple processor like what you'd find on a cell phone, and but they really want to do something very that involves a lot of computation, right? Like say translate one language to another, which actually takes a lot of compute. And so the flow of what would happen there is really the guy. I mean, the person goes in, he wants to translate something, and then it goes through this massive 4G network, which also has a lot of processing, which we're not talking about today, but uh, yeah, I mean, this also has a lot of processing in terms of taking these signals, converting it into a form that the data center on the other side can understand, and all of that goes on here. So there's a big cloud of this. And then eventually at some point, a bunch of network packets with the request that this person is trying to get translated shows up at a data center, right? And the data center runs a lot of processing on this, and then eventually it needs to return it back as a packet to this 4G processing setup, and then it has to show up on the person's phone, right? And so if you kind of try to measure the latency of the system, you can measure it from the start here, which is the point at which this guy kind of clicked enter on his phone or whatever, and to the point where it kind of did this complete round trip, right? And so in terms of what business people or people who design this want is, it's, I guess the thing we've heard is it's very, very hard to keep someone's attention if this takes more than a few seconds, maybe 2-3 seconds, and so that becomes a very challenging problem, because you have to kind of factor in all of this processing, and once you separate out what happens here and for those signals to travel and go to the data center and come back, you get a very, very small 1 or 2 seconds to process this in the data center itself from the time the request actually hit the server to responding with the result, right? And the thing that makes this even more complicated is you're not doing this for one user, but at any point in time, you're probably having multiple millions of users trying to do this on a data center, right? So you've got maybe a few thousand or a few lakh users on this side, and then you've got to meet that latency requirements of a few seconds on for each one of those people, right? At least for 95% of them or something, right? So what I guess what this kind of flips the whole thing that we know about software, right? So usually when we talk about software, the main focus is on getting it to work correctly, whether it's a database or any application software. Typically, want to get it to work correctly first, and performance becomes a second aspect. But in this setup where you've got kind of these real-time tasks, if it's functionally correct and you don't do it within that 3 or 4 seconds that you get, then it's not very useful, right? So that point it becomes a failed system. And there are cases where, say, for people like Netflix or Amazon or the people who are doing streaming, for them, they don't mind if you actually at some point you say, okay, I don't have enough processing, so I'm going to show you slightly lower quality video, but I'm going to show it to you on time, right? So in some of these cases, doing this on time within the latency constraints becomes more important than the actual quality of the solution, right? So just this kind of a use case which stresses the importance of why you want to make your systems really, really fast and really, really performant, right? So, okay. So that being said, let me just move to the next slide. Okay, sorry. Okay, so yeah, I think that's all I wanted to say here. Okay, so once we kind of try to peel this a little bit further, right? So I'm going to focus on, I'm going to largely ignore the piece here. I'm going to focus on what happens when it hits the data center right here to it actually sending the response back, right? So if you start focusing there, there are again two pieces here. So from the external network, you've got the data center itself is a huge network of machines with lots of racks and all of them connected through networking equipment, right? So what happens is as soon as you get into the data center, whether it's Google or any of the big data centers, there's a front end set of servers sitting there, right? And there's a large internal network. So what the front end servers try to do is they look at the requests and then they see what machines are available and try to kind of send the request to the right machine or to the machine that's free, right? And And so there's a bunch of trade-offs there where, okay, you don't want to load one machine too much, so you want to kind of split the work across multiple machines, right? Then some of these machines fail frequently, so you have to factor in what percentage of machines are actually up and how many failed, right? And the network itself sometimes tends to have congestion and other issues. So there are people who, there are dedicated network performance teams which look at, okay, what is happening in the network, are switches going bad and all of that. So that's kind of one side of the engineering that goes on from a pure performance perspective. And once the task itself comes and hits the machine, so if you kind of submitted the task, you've identified the machine, and now it's gone and it's hit a machine, right? Then the machine, from that point, that particular computer needs to do a lot of processing, right? And basically, first it needs to get all of this. First, it needs to look at the network packets that are coming in and understand, okay, what is this? What kind of a network packet is this? So that is really the packet processing front end. Then if you're doing, I just took the translation example here. There's going to be a bunch of uh, people looking at, okay, so first, has this person spelled the thing correctly? What word is this? Which language is this? All of that lookup happens. Then you have a machine learning algorithm which kind of takes the network in one language and translates it into another language. Right? And finally, you have to do kind of a lookup of the results to convert whatever your machine learning algorithm is translated into a bunch of words in the other language. And then you kind of take all that information together, convert it into network packets, and then send it out through this network. Right? And I'm not going to concentrate much here. We can, I mean, there could be references and other things, but I'm not going to really concentrate much here today. I'm going to predominantly concentrate on this part. And the key is really from the point that you actually receive this to you to send the results out, it has to happen under a second of latency. I mean, in some cases it can even be much lower than this. So I'll kind of concentrate mostly on what happens here and what all things enable us to get to this latency and what are the open problems there, right? So, okay. Are there any questions? Or? Okay, let me keep going there. Okay. All right. So if you kind of look at the front part of that pipeline, right? So the first step is what we talked about is the packet processing, right? So you have a network packet that has come to the system. Basically, this is a computer sitting there, and you have a network packet that has come there. And what the packet processing front end tries to figure out is, okay, I've seen this network packet. It's got all these bytes in it. So it needs to look through this network packet and figure out, okay, this is a network packet that is destined for this application which does the translation, right? And so it has to then send that network packet to the correct application, right? So that's how it does it. So on a given machine, you can have multiple different applications running sometimes. So you could have an application doing translation, you can have an application doing, say, image classification, some application doing video stuff, and all of that in the same machine. And so what the front end is really trying, the packet processing is trying to do is, from the bytes of the packet that you've got there, it looks at it and then it figures out, okay, this is a packet that is a request for a translation, and so I have to send it to the application that is doing the translation. So, and this actually ends up being extremely compute intensive. So there's a lot of math operations you need to do on the CPU itself to get this done, right? And I've listed out a few of these here. So first is you need to first check, okay, so this packet has taken a long path on the network to come from where it started to where it is reaching. So it needs to first figure out, is there any corruption in the packet? Is there some bits that got flipped? So there's a bunch of error checking algorithms that happen. Second is sometimes it needs to figure out, okay, where did this come from? who is the sender, who's the receiver, and all of the details there. And so there's kind of a bunch of headers in the packet, and so it looks at the headers and it needs to process those headers, right? So it's very common for you to have, specifically in data centers and people getting large volume of requests, for you to lose some packets. And so it needs to kind of look at, so for instance, you could have sent packet 100, or packet 101, 102, and then you would have received 100 and 102 might have got lost. Then, so it needs to look at that and it needs to figure out, okay, I got 100, I got 102, which means that 101 got lost somewhere. And so that needs to be done. So have I lost something? And do I need to ask for that again, right? So that needs to happen. And then finally, once it figures out, okay, I've got the right packet, there's no error, it's coming from the right people, then it finally kind of extracts the data from that network packet and puts it into the buffer that the application uses, right? And so it has to kind of copy the data from wherever the packet was put to whatever the buffer that the memory region that the application is using. And so there's all of this that happens. And clearly, if you want to keep the problem about doing all of this on your CPUs, you waste a lot of time doing this, and sometimes the CPU is not the best place to do this on, right? And so there's like a lot of innovations that have emerged in the last, I think it's become very popular in the last 5-6 years, where you kind of try to do this somewhere else and not on the CPU. So I've listed a few of that here. I'm not going to go into the details of each one of these, but I can send in references definitely if it will be useful. But yeah, so the first thing is basically what they call RDMA, and okay, so yeah, so let me just share this. Okay. So the first one is basically RDMA, where so what RDMA is the card that does the network processing itself. It takes some of these functionalities. For instance, it might be able to do this copy. It might be able to make sure you didn't lose anything. So a lot of this might be done on the network card that you actually plug in your Ethernet port into. So that way the CPU does not do a lot of this work, and the CPU can do other things, right? So that's kind of very popular technique. I think a few companies, especially Mellanox and a few of the other companies, specialize in doing chips for this, right? The second one is, I mean, given all the security concerns, some people want to do encryption of these packets so that if someone actually reads the packet in the middle, they can't guess what is going on. So you see a lot. I mean, there's a lot of solutions that use FPGAs. So FPGAs is essentially a hardware chip that kind of is very good at doing these bit level or network level processing. And so there's a bunch of companies that, I think Xilinx, Altera, these are companies that produce these FPGA chips, which can do some of this without really keeping that on the CPU. And then the last thing that we've seen a lot of recently is where, so what happens is you have to do this list of steps for every packet, right? And so it's always better for you to have larger packets than smaller packets, because for instance, if I'm trying to send, say, 40 kilobytes of data, right? If I have 4 kilobyte packets, then I have to do this 10 times for that 4 kilobytes of packets, right? But if I have a really large 40 kilobyte packet, then it shows up as one packet and I have to just do this once, right? And so there are techniques where people say, okay, I know the end processing is going to be very difficult, so there'll be a piece of hardware that sit in the middle of the network and combine, say, 10 different packets that go to the same endpoint as a bigger packet, right? And so that again saves processing time. So yeah, I mean, so in terms of if you look at a typical data center, there's a lot of time spent on just looking at the network card and trying to figure out what is coming on the network and sending it to the right people. And so any kind of research or innovation that helps either making that faster by offloading it to the right pieces of hardware, or kind of intelligent algorithms that avoid some of these processing is very useful, right? And that's always been a kind of a very active area of research. So let me, okay. Okay. Yeah, so if you have any questions or if you want me to talk about anything in detail, just feel free to interrupt and we can just, yeah. So I'm just going to go through the next one. So, okay, so what happened in this flow is basically, okay, so now you've come here, you sent it to the right machine. That machine has processed the packet, and it's going to the next stage where it's figured out, okay, this is the packet for the translation application. So so it's been sent up to the translation application, and so now you want to kind of actually translate this from from whatever language. Say you're doing English to Tamil or something like that, then kind of you got the English sentence and you're trying to put it to the machine learning model now to translate it to the other language, right? So that step, what happens is so this is kind of what happens when you try to execute the machine learning language model on the system, right? So first, someone kind of an expert in, say, translation or whatever, that particular machine learning model has defined a model which kind of says, okay, here are your inputs, here are your outputs, and these are the operations you do. For instance, if you take this graph, he said, okay, have a weight matrix. I have a matrix which specifies the input, and I'm going to multiply it, and then I'm going to add it with another smaller matrix, do some exponentiation or some other function on it, and then I'm going to give you the result. And that result represents the translation from one language to the other, right? So what happens is, someone some machine learning expert or data scientist has kind of coded this up either in Python specifying this graph, or he's just used some kind of a visual interface where he can drag and drop these things, right? And then to create a model for you, say like in MATLAB or something like that, right? So then the moment he gives you this model, then it becomes the job of the system software, all the hardware, to really take this model and execute it and say whatever is the best or the fastest way to execute it, right? And so for that, you're going to go through a bunch of steps, right? So try to kind of highlight some of the important steps. So each one of this is probably multiple hours of learning by themselves, right? So I'm not going to go into the details of that, but again, if I can point to references and stuff. So, but what happens at a high level is someone has specified a graph which represents a machine learning model, and we're going to run it on one of the frameworks, right? Which I just picked TensorFlow here because it's probably the most popular one. So you're going to run this graph using TensorFlow, right? And the TensorFlow runtime itself solves a lot of the problems, right? So first, if I look at this graph and I want to execute it, the first thing I want to do is basically, okay, there are these three variables, right? There's a weight variable, which will be probably some kind of a matrix. There's an input variable, which is again some kind of a matrix, and then there's this bias, which is also a matrix. So first I'll have to figure out where do I allocate the memory for each one of these, right? And so there's kind of a memory allocator within TensorFlow, which looks at this and says, okay, let me allocate so much memory on the CPU and so much memory somewhere else, right? And then the moment you've allocated all of those memory objects, then you want to kind of schedule this computation graph through this on this compute unit, right? Which is again either CPU or some other accelerator. So something within TensorFlow sits in and decides, okay, these are the sequence of operations I need to do and he starts scheduling it either on the CPU or on the GPU, right? And so there's that scheduler, right? And finally, all of that gets executed and you get the results back. There are cases where you schedule something on the CPU, you want to move it over to the GPU, then kind of use this bus to move things around, right? And so in a lot of ways, the real hard parts of executing this is taken care of by the framework itself and by TensorFlow or PyTorch, right? In terms of how to execute this, where to execute what, where to allocate what, and making sure all of this works correctly and you get the results back, right? So that's kind of what happens under the hood when you kind of take a machine learning model and try to run it through the system, right? So, yeah. So let me. Okay. Now, okay. So there are most of the times the frameworks themselves kind of do a pretty decent job of trying to figure out what is the best way to schedule these things on these systems, but there are still kind of open research problems here, right? So first is there's a scheduling problem of trying to figure out where to schedule what, which ones you want to schedule on CPU, which ones you want to schedule on the accelerator, at what timings and all of that. So there's that heterogeneous scheduling problem. The other problem is this graph optimizations. I'll talk through that in the next slide. So just like you want to figure out which operations schedule where, there's also the problem of trying to figure out which type of memory do you allocate where and how do you move it. So there's that memory allocation problem. There's a bunch of optimizations around it. And then both of these pieces, right, both the CPU and the accelerator itself, there's just been a lot of innovation there in the last 5-6 years about, okay, how do I run these machine learning workloads better and how do I get it to run faster, right? And so there's so I'll talk a little bit about that also in terms of, okay, how has these platforms, both CPU and GPU, changed for these workloads as such, right? So yeah. But at a broad sense, in terms of taking machine learning models and executing it on one of these platforms, these are kind of the big open problems, right? So, okay. Right. So let me. Okay, so I think we kind of talked about what graph optimization is. So basically, let's say the data scientist or kind of the expert gave you this graph, right, where he said, okay, I want to take these two matrices, I want to multiply them together, and then I want to apply this tan h function on this multiplied result, and then I want to output the value. Right. So if I go and get this to, I just execute this as it is, right? What will happen is, okay, so first you fetch the weight matrix, you fetch the other matrix, and then you multiply them. Then the multiply itself will write its result out into memory, right? And then the next guy comes out, the next guy is kind of the tan h. He's going to read the value that this guy wrote into memory. And eventually he's going to do his operation and then he's going to write into memory, right? The result into memory. So what happens is you've got like one write, one read, and then another write. So I have to count this also. So the two reads, an intermediate read, so the three reads and two writes, right? And like we know in computer architecture, writes and reads to memory are extremely slow, right? So we want to avoid this as much as possible, right? So what happens is there's a big compiler that sits in front of before you execute anything, and what it'll do is it'll look at cases like this and said, okay, I don't want to do this middle write to memory and then read it back, right? So what it'll do is it'll kind of say, okay, let's just combine these two into one big operation without really writing to memory in the middle, right? And so So what happens here is now all you do is you read the weight, you read the X, you do the mul and the tannage together, and then you write the results exactly once, right? So you save one intermediate read and one intermediate write, which translates to a lot of cycles, right? So CPU cycles, and so this typically you see when you apply this big graph optimization, typically you see somewhere between a 50 to 60% increase in performance, right? And I mean, lot of the graph stuff that we use to today, the graph compilers in TensorFlow and PyTorch, they can do this reasonably well, but there is still a lot of holes, and people do a lot of research in terms of how to make this better, right? So, but the good thing is that what they're doing currently in terms of code is already available. So, yeah. Okay. So I don't know why this showed up, but okay. Okay, so that's kind of the taking of these two, right? Now, if you go into the hardware itself, right? So what happened is kind of in the last 3 or 4 years, you've seen a lot more people use. I mean, lot more features added in both CPUs and GPUs for making machine learning go much faster. And I have some performance numbers later in the slides, right? So first is basically when you start looking at some of these machine learning workloads and what they do very frequently, right? Because you want to kind of make the thing that it does very, very often fast, right? And so the one thing that you see machine learning workloads do more and more is kind of just do a lot of matrix multiplies, right? And so if you're a CPU designer or if you're someone who's designing GPUs, to make these workloads go faster, you want to kind of make your matrix multiplies or your multiplies go very, very fast, right? So if you take a single CPU core from any of the manufacturers today, it can do somewhere between 40 billion to 75 billion operations per second, which is probably about 4 to 6 times faster than what it was 3 years back, right? On the GPU side, it's gone way more faster. The flagship GPU from NVIDIA can do actually 31 trillion operations per second, which was roughly kind of the throughput or the performance of 2 big racks of servers, right? Which is like probably 200, 300 servers, and you can get that on a single card today, right? So there are very, very specialized features on every generation that all of these, both CPUs, GPUs, and everything that you run your computer on, add on every generation, right? And yeah, I mean, I'm not going to go into the details because that will probably become very easy computer arch specific. So again, if there's interest, I can send another presentation that covers some of these details. But yeah, I mean, but basically, in the last 3-4 years, maybe in the last 4-5 years, what CPUs and GPUs can do to make these things go faster has probably increased about 8 to 10x. So that's one of the reasons that we can do a lot of these machine learning like workloads in real time today, right? So okay, so we've kind of covered. Yeah, just to go give you a recap, right? So what we've covered is we've kind of said, okay, someone gave you a model, you wanted to put this through this framework, and the framework took care of where to execute what, where to allocate what memory, how to allocate, how to run it, and all of that. And we looked at some techniques which can make this go very, very fast, broadly, right? So another class of research topics that people have kind of looked at very recently is, okay, can I design this piece to go? Okay, so earlier what people used to do is, okay, I'm going to design a machine learning model that can get me the best accuracy on, say, translating this, and I don't care about how fast it can execute, right? So someone who's completely outside the performance domain kind of designs these neural networks or these algorithms, and then eventually you kind of do a bunch of optimization, you do changes on it, you kind of try to execute it on different types of hardware and try to get it under that 1 second or whatever latency constraint that we talked about, right? And so these two become fairly independent processes typically. Someone kind of designs a model, largest model he can get away with, and then it becomes a job of the hardware and the performance and the other people to kind of make sure it hits the targets, right? One kind of trend that is emerging very recently is for people to say, okay, can I build algorithms that kind of are maybe instead of being 99% accurate, maybe are say 97% accurate, but 5 times faster or 10 times faster because I have to do less things, right? And so there are kind of, that's a very, very active area of research. We don't see this much in production today. Not that I know of, there could be people using it in production, but it's a very active area in terms of research, right? So the two things that you see very commonly there are kind of what people call distillation techniques and compression and sparsity techniques. So I'll talk through a couple of this, right? So what distillation is kind of what you do is you have a problem, say you are trying to say build a machine learning algorithm or a neural network that can translate from one language to another, right? So the first time when you're trying to explore this problem, you want to throw the biggest network that you can possibly throw, right? So you might say on the left, what I have here is a network that does say translation but uses 4 billion weights, right? And you will train this on say something with a million sentences or something like that, right? And so you did this, you trained this model and it's doing well, you get 99%, 95, 99% accuracy, right? Now the problem is when you want to go and use this network in actual production, the problem is this is too big, right? And so if I have to kind of put an input through this and get an output from this, it's going to take me 5 seconds, and that is not acceptable in production, right? And so then what people try to do is, okay, I have this big network. Can I have it teach a smaller network which has lesser weights, looks smaller, and can execute faster the same thing, right? And so what you do is you kind of have this big network, you've trained it fully, and then you have this other smaller network which can execute fast. It has less parameters. It's good for production, and then you kind of take some of the intermediate values from this network and then try to train this network. I don't understand the math of how this works, but the end product is basically you get kind of from a 4 billion weight network, you get a 0.25 billion weight network, which is probably 16 times smaller, which means that it will take 1/16 or 1/32 times the amount of time, and but kind of gives you almost the accuracy as the big one, right? And so this is kind of becoming a very, very popular technique. So people train a big model and then they kind of distill it down to a smaller model that does the same level of accuracy, right? So this is, it's a very, very active area of research, and we see people kind of using this in a lot of places, right? So that's one place. And then the second one is what people try to do is they say, okay, I've got this network. I know, so a neural network can be represented as kind of all these. So these are neurons, and then you've got connections between these neurons, which is the weights, right? And the size of a neural network is proportional to how many of these lines you have, because each one needs to be represented by a weight. So one common technique you see is people say, okay, not all of these weights are very important for my accuracy. So I'm going to throw away some of these weights, right? And so you took some of these connections and you just threw them away, right? And that process is called pruning, right? So the advantage about throwing away some of these weights is now, because you have zeros here, you don't have to store those zeros, right? And so your network again becomes very relatively small. right? And so there are some places where people have shown that, okay, I can take these weights and throw away 90%. So if this was, say, a 400 megabyte network, then this will become a 40 megabyte network, one-tenth the size, and you don't lose much accuracy. And so moment this becomes small, you can actually execute it much faster. Right? And so that's kind of the other piece that you can see sometimes, right? So okay, so yeah, so I think with that I kind of finished all the things around latency. Is there any questions, or can I just pause maybe for a couple of minutes? Just okay, all right. Okay. Okay, just a second. Sorry, just a second. I just need to just give me 1 minute. I'll just get some water and come back, sir.
Participants can post your questions in the chat.
Hello, sorry. Okay, so I think there's a question about TPU. Okay, can you hear me?
Yes, yes.
Okay, nice. Okay, all right. So I'll talk about the TPU maybe towards the end when we get to training. Right. So yeah, I mean it's not okay. Let me. Okay. All right. So I think we kind of walked through the latency problem. Okay, so the next one is the throughput problem, right? Which is okay. So I think what we were covering here is you already had the machine learning model. You were kind of talking about, okay, how do I use it to serve predictions to a lot of people at the same time, right? So it's kind of the inference problem that we were talking about all through this, right? And that has very, very strong latency constraints, right? So the flip side to that is how do you train these models, right? And so when you want to train these models at that point, it's not a latency problem because you're not worried about every request. You're not worried about trying to keep every user happy and keeping them under that 2 or 3 second interval, right? What you're worried about is, okay, how fast can I train this model, right? And okay, is there a question? Sorry. Okay, sorry, no, I just saw a raised hand, so I just okay. All right. So okay, so what you're trying to do is you're trying to train this model in terms of trying to understand okay, how do I build this model, right? How do I train it from scratch? And so the property of training is first you have a very, very large data set which has examples, right? So I'm dealing with supervised learning here, so there's like examples that you choose to train. So for instance, you might have a few images and then you have something which says how many what kind of, is this a cat, is this a dog, whatever, right? And so one of that data set is the ImageNet, which I think is very popular. And then I mean, so ImageNet actually has about 14 million images, which is a lot. I mean, if you think about it, it's a lot of images that you use for training. And then there's this other popular training data set, which kind of people use to train all the language networks, which has kind of sentences from English to German or German to English, and that has about, I think, if you leave everything out, the smallest one is about 2 million sentences. Uh, so so at this point, the training and the inference has got so good is that both in inference and in classification, machine learning models tend to beat humans in terms of the average accuracy score, right? And what you need to do is to achieve this level of accuracy, you need to go through about 500,000 iterations. I've just picked this number up. It's usually much higher than this, but what I mean by an iteration is you select a random number of images from this and run it through the network once forward and then once backward, which is a lot of matrix multiplies. And you have to do that about 500,000 times before you get a decent model, right? And so if I take the smallest model that we know, right, and say you try to do this on a desktop, right, a good powerful desktop, right, say 16 core, whatever desktop, right, that you have, this will take about 90 days, right? And for some of the models, bigger models, it might be like 6 months to actually do this, right? And if you take a GPU, which is really the graphics processing unit, right? It's just like what you run games on. That will take about 3 hours, right? So it's a big factor of speed up when you do this actually on a GPU, right? And people have been trying to kind of establish world records around this. All the hardware companies do this, and so kind of I think the best record that I could see today in terms of how fast you can train this model is about 48 seconds, right? So if you have a desktop, it takes about 90 days, and if you have the best in class hardware and the right software stack, it takes about 48 seconds, right? And so kind of there's a lot of innovation both in hardware and software that goes on to kind of really take this and drop it down here, right, into this, and so I'll briefly touch on a few of those, right? So okay. I can see, I don't know if there are questions. I can see two raised hands. Are there any questions?
For congestion control in large networks, what is the role of active queue management? This is one question in the chat from Mr. Kirti Pati.
Okay, so this. Okay, so yeah, okay, that's a good. Okay, so can you repeat it? So you're saying active queue management, or?
Yeah, for congestion control in large networks, what is the role of active queue management?
Yeah, so you can actually do it both in terms of, so when you want to do congestion control, you can do it at different parts of the network, right? So one is the most simplest way is where your endpoint tells the other endpoint that, okay, I'm losing packets, so send slower, right? And so that is the classic where TCP, you kind of tell the other guy that, okay, I lost so many packets, so can you send slower, right? So that is one way of trying to do that. The other is in the middle points, which is your network switches and all of this, where you see packet drops, they can actually just signal the previous guy on that route that I lost a packet, or this is the rate at which I lose the packet. And this actually happens on not your main network interface, but some signals on the sideband, right? So the biggest challenge in congestion control is I have my network fully filled up, right? Now, so A is sending to B, and I have the path between A and B fully filled up, right? And now if I want to convey the message that, and it's also likely sometimes that the path from B to A is also fully filled up, right? So if I have to let A know that, okay, I'm dropping packets, it's sending too fast, then I can't send it to the same network on which is already congested, because the message that you're sending that, okay, the network is congested, sometimes can get dropped as well, right? And so there's a combination of both of these end-to-end where you send it on the same network, and there's also techniques where you just tell the guy just before you're using some sidebands, right, to say there's congestion in the network, right? So I don't know. I mean, it's probably a long answer. I don't know if it answered the question. So. Any other questions, or should I proceed?
Next question is from Mr. Vidyasagar. How do we predict maximum workload within brackets jobs can give given to the machine?
Right. So it really depends on the type of workload, right? So the ones that we're talking about in terms of the neural networks ones, most of the time they take the same amount of time. Whether you so the thing is, if you have a given network, you do the same sequence of operations again and again, and it's very easy to predict those kind of workloads. What will be the worst case time, right? But in some of the workloads, say for databases and other things, it's very hard because sometimes what happens is you hit in the DRAM itself, and it's much faster. It'll take you maybe a few microseconds to get the data, but sometimes you might have to go all the way to disk, and it takes kind of maybe multiple milliseconds to get the data, right? And so yeah, that's a challenge. And what people try to do is instead of trying to actually provision for the absolute worst case, right, where you said, okay, this query is going to take 100 milliseconds because it went to disk, you try to ensure about a 95% hit rate in your DRAM, right? So then what happens is, for 95% of the people, you're going to give that back in about 5-10 microseconds, and so they're going to be happy, right? So very rarely people try to optimize for the absolute worst case latency. They try to optimize for the 95th person, right? And so that's how we avoid that problem. So that's it. Anything else?
Please suggest some open source softwares to train our students.
Yeah, okay, so I have some of that in the end, but yeah, I think depending on where you want to get into the stack, right? So let's talk through software here, right? So first, depending on where you want to really concentrate here, right? So obviously all of this is, again, most of the models are available online. If you go to the TensorFlow Model Zoo or the PyTorch Model Zoo, you can see all of these models, right? All the Python code is available there. So the model zoos have this. This one, if you want to kind of look at how to use this optimizer graph, I think it's called XLA. I'll probably send Prasanna a note afterwards, but there's a compiler called XLA which does this for TensorFlow, and you can again get the source code of that. You can learn how to run that. Right? This TensorFlow is completely open source again. PyTorch is also open source, so you can kind of get in there and you can see how some of this works or how to use it again, right? This side again, I think there are multiple ways to do high performance on the CPU. There's OpenMP, MPI, which again a lot of the HPC people use. So that's and then there's a few libraries that run very fast on the CPU. There's something called Bliss. So this side again, there's a bunch of open source software here. This side is a little more tricky. Basically, you need to kind of get into. There's a couple of very, very good Coda books and Coda material about how to program the GPU, and so that's the other. And again, you can also look at, if you go within TensorFlow's source code, for each one of these operations. For instance, for a matrix multiply, you can get the code of how did they write it to run on a GPU, right? And so that will be kind of most of the open source software, right? So depending on which aspect of this you want to concentrate on, whether you want to concentrate on the compilers, or you want to concentrate on the algorithms themselves, or you want to concentrate on the architecture and closer to the metal, then all of this has multiple open source software versions. And I'll send the names. I don't have it in this presentation, but I can send the names to Prasanna and she can kind of, yeah, so.
They've requested for the PPT. So So probably you can add the names at the end and you can share the PPT.
Yeah, I'll do that. Yeah, I'll just append it to the slide. It might be
Okay.
easier.
One last question. I think that is already answered. Question is from Dr. Shilpi. How to achieve higher accuracy through machine learning? I think you have already answered it, right?
Right. Yeah. I mean, basically, I guess the short answer would be kind of bigger models with more data give you the best accuracy, right? And but the problem is really where to make that cutoff, right? And so, for instance, if I train this instead of 14 million, I train it on 28 million images, it'll probably give me very good accuracy, but then my training time shoots up. So that's where the trade-off is. It's really a performance versus accuracy trade-offs. I mean, and I think the general consensus is uh, smarter algorithms with less data versus lots of data with basic algorithms. If you compare those two, lots of data with even basic algorithms do tend to do very well. So a lot of times it's about having very high quality data to train your models. So, right. Okay. Okay. The questions are, should I? Okay, maybe I'll keep going and you can interrupt me if there's any questions. Right. So yeah, I think what we were talking about was in terms of training time and how it's impossible to do it without specialized hardware, right? So, okay. So I think one of the things is I just wanted to put this just as a broad understanding, right? So what makes a GPU to reduce this from a 90 days to 3 hours, right? And it's not. I mean, it's not. Yeah, there's no magic there, right? Basically, what happens is the GPU has lots and lots of independent cores, right? So if you look at a modern GPU, there's something like 5,000 cores on it, and if you compare it to a typical desktop, you can probably stretch it to about 8 to 16 cores, right? If you get a very high end desktop. And in terms of the price, a GPU will probably cost you about 300, 15,000 rupees, and this would probably be about, they're very comparable in terms of price, but this GPU does have a lot more cores, right? And so that's what makes it very fast. Right? The second thing that these accelerators and the graphics units actually do very well is they have a lot of these specialized things that can do matrix multiplies very fast. So if you take a given size of matrix multiply, a large matrix multiply, a GPU can actually do it about 32 times faster than a big desktop, right? And so that's where all the speed up comes. And the reason why people, I mean, why every workload or everyone out there don't move to GPUs and we just kind of, you don't see them everywhere is the main challenge is programming any of these accelerators is extremely tough. For instance, if you write code and you saw a segmentation fault, it's very difficult to figure out where the segmentation fault came from, right? So kind of if you want to really get into that area, right, trying to figure out, okay, I want to become very good at programming these accelerators or CPU, the first place to start out is to have very good C++ skills, right? C++, OpenMP, parallel programming with C++ skills, right? And at least in the lower side of the algorithmic side of the world, Python has become the de facto, but moment you get closer to metal, C++ has become the standard, right? And so kind of you'll see a lot of these frameworks and all of this written in C++. Right? So that's kind of the first barrier, right? You need to be really good at C++. And then the second is there's a bunch of training material from NVIDIA and AMD on basics of how GPUs work, and getting a good understanding of that is important because unless you understand how the GPUs work, it's very hard to program a GPU, right? And the final is there's a lot of CUDA or OpenCL code out there, and you can start out kind of looking at the code, executing it, and seeing what happens. There's profilers and other things that let you see what happens as you execute the code, and that's a good starting point in terms of being getting to be good at programming in a GPU, right? So roughly, I guess if I had to put it right, if someone has to write something as maybe a simple vector matrix multiply, if it takes in a few days on a CPU, it will probably be multiple weeks on a GPU, right? And so that's the real challenge. It's kind of trying to write it, then tune it, and then make sure you get the performance, and then trying to understand what is going wrong, right? And so yeah, that's kind of the big challenge. So they fast, they go very fast, and but it requires very very specialized skills to be able to program them. Right? So okay, there I think I saw a couple of raised hands. Was there any questions?
I
Okay,
think there's
let
no
me
more
just.
questions. Yeah, please
Okay.
continue. Sorry.
Okay, so I think I just wanted to show that. So people a lot of times just talk about hardware and why hardware makes all of these things very fast, right? But the key is really having good high performance software. So what I'm showing here is a translation model, and this was kind of work that multiple companies did over the course of a year, right? And so when someone started this model out, it took about 1,400 seconds to train, which is roughly maybe half an hour. Yeah, half an hour. So about half an hour to train, right, on an 8 GPU system, right? And so then a couple of people took that algorithm, they improved it, they changed the math it was doing, they kind of changed things there, and then they were able to drop it from the half an hour here to about 495 seconds, which is roughly a little less than 10 minutes, right? Which is a 3x speed up, right? And then what people said was, okay, let me try and hit the world record with this, right? So then they said, okay, I'm parallelizing this across 8 GPUs. Let me figure out a way to parallelize this across a lot more GPUs, and added a lot of software changes to do that. And then over the course of 6 months, with the similar hardware, no hardware changes, the thing kind of dropped from to about 32 seconds, which is from where you started off at 1,400 seconds to 32 seconds. By kind of writing really good software, you get about 44 times speed up, right? Which is pretty high, right? And I've listed some of the optimizations you did here, but I'm not going to go into the details. So yeah, right. I think this is kind of my last slide. So yeah, I mean, I think just we've seen what happens with models today, and so both in terms of systems and algorithms, I'm just trying to list out what will happen, what is likely to happen in the next few years, right? So first is, I think, a big trend is people are trying to use these machine learning algorithms for increasingly complex tasks, right? So in the last 5 years, I think what you see is people trying to use these networks mainly for image classification. That is to say, whether this kind of is this a dog, is this a cat, whatever, right? And then for translation, and today, if you kind of look at these two, they've really plateaued, right? I mean, you're close to about 90-95% accuracy on this, and this can kind of on translation you can do much better than humans. So it's really starting to plateau, right? So the question answers and automatic knowledge, which is again in an area where you have automatic chatbots and other things, that has also started to become very very good. So really these three, I think you'll find less networks being proposed in these three areas as you go forward. And these networks tend to be about a gigabyte in size, right? So what is happening right now is people are trying to use neural networks in areas that are kind of adjacent but are important, right? So one is kind of this recommender systems, which is trying to predict what item a given person will like or what movie he's likely to use, and those models tend to be very very large. I mean, I've seen models of 64, 128 GB sizes, which is a very very big model, right? And so that is one application area that's emerging. The second one is getting AI to kind of do tasks by itself, right? Like in robotics or getting AI to play a game by itself, and that's kind of this reinforcement learning area, and this is the OpenAI gym is kind of an open source software where you can play around with all of these reinforcement learning algorithms, right? And the third one is, I think, like we were talking earlier, I think generally more than algorithms, it's the amount of data you have that makes a big difference. And so getting high quality supervised data is very, very difficult, right? And so people are trying to look at techniques where 50, 100 of the data I'm using, 80% or 50% is really, really high quality, but I have this noisy and potentially badly labeled data. How do I use both of them so that I get a bigger data set, right? And so that's the three things I'm kind of seeing emerge quite a bit. But yeah, there might be others, but yeah, this is what I could think of. So yeah, I think that's all I had. So
No more questions, so I think we can wind up.
okay, all right, yeah, thank you.
Thank you. So once again, on behalf of CSE department, I thank you, Ramkumar, for taking your time off your busy schedules and sharing a few open-ended research problems to the participants over here. I'm sure the faculty is interested in machine learning and deep learning. Like nowadays, most of the faculties take up their research in deep learning. So they have also got some insights and good takeaways in the areas of application of computer system architecture. So thank you very much for your time once again. I also thank the participants for your patient listening. I request the participants to fill in the feedback form, which is posted in the chat box. And the feedback form will be open for the next 1 hour only. The PPT as requested will be shared by us to all the participants in the mail. So thank you all once again. Thank you.
Thanks. Yeah.
Thanks,
Bye.
Ramkumar.